Here are two diagrams shown which will illustrate the concept of using constrained motion equations. So basically, in this particular diagram, this is the pulley, that is the fixed pulley P, and this is a movable pulley. I am labeling it to be P1. So let me mark out the distances that we are going to use while using constrained motion. The distance of the center of this pulley from the rigid support happens to be xp1. So this distance is xp1. So this distance will correspond to the variation of the length of this particular string. Let me label the masses. So this is mass m1, this is mass m2, and this is mass m3. The distance of m1 from the rigid support is x1. The distance of m2 from the rigid support happens to be x2, and the distance of m3 from the rigid support happens to be x3. So we are taking the distances from the center of mass of each of the blocks. However, here we will also consider that these are point objects, so the center of mass and the location of the point object is one and the same. So this happens to be x1, this happens to be x2, and this happens to be x3. Now, while writing the constrained motion equations, we need to conserve the length of the string. So as you can see over here, that this string that passes over the pulley P1, its length can be calculated as x1 minus xp1, which is this part. The left hand side part can be said to be x1 minus xp1. This right hand side part, this can be said to be x2 minus xp1. And the part that passes over the pulley is constant, that is pi r, that will get differentiated out to be 0. So we are not going to bother about that particular part. So while writing down the equations, I can write down x1 minus xp1 plus x2 minus xp1 equal to length of string 1, L1. So if I differentiate this, I get a1 plus a2 minus 2ap1 equal to 0 on double differentiating. Now for the string 2, we can understand that this is nothing but xp1 and this is x3. So we can simply write down for the string 2, xp1 plus x3 happens to be a constant L2, let's say the length of string 2. So after double differentiating these, we get ap1 plus a3 equal to 0. In order to simplify, we multiply this equation with 2. Then we can write down 2ap1 plus 2a3 equal to 0. Adding these two equations, this one and this one, if we do add these two equations, then we get the constraint motion relation 2ap1. Here it's 2ap1. Okay. So if we add these two aforementioned equations, namely this and this, then we get the constraint motion relation. By the cancellation of 2ap1, we get a1 plus a2 plus 2a3 equal to 0. So this is the constraint motion relation that we were seeking. Now as you might be aware that when we use constraint motion relations like this, then it is important to take A1, A2 and A3 in the same sense with respect to the rigid support, meaning all have to be going away from the rigid support or all have to be coming towards the rigid support. So let me here choose all of them to be going away from the rigid support. So this is A1 going away, this is A2 going away from rigid support, and this is A3. The tension in the rope L1 is going to be T, and the tension in the rope L2 is going to be 2T, because the pulley P1 is massless. So a massless pulley has to have zero net force on it. Analyzing the block M1, we get M1G minus T is equal to M1A1. It's clear that at least one of A1, A2 and A3 is going to be negative. So all three of them cannot have the same sign because they are effectively adding out to be 0. So M1G minus T is equal to M1A1. M2G minus T is equal to M2A2, and then the third equation, which is M3G minus 2T is equal to M3A3. So these four equations will give us the answer for the four unknowns A1, A2, A3 and T in this particular situation. Now let us look at the second diagram drawn over here. So this is the pulley P, this is the pulley P1, and this is the pulley P2. The pulley P is fixed and P1 and P2 are movable pulleys. So the distance of the movable pulleys from the rigid support is taken to be XP1 and XP2. So this is XP1 and this is XP2. Now all the masses, the distance of all the masses from the rigid support is labeled according to the labeling of the masses. So the masses are M1, M2, M3, M4. So these are the four masses. Let us take the distance of M1 from the rigid support to be X1, M2 till the rigid support to be X2, M3 till the rigid support to be X3, and M4 till the rigid support to be X4. So this is X1, this is X2, this is X3 and this is X4. These are the distances as shown. On analyzing the constrained motion relation, here there happen to be 3 strings instead of 2. So let me label the strings as well. So let this be string 1, let this be string 2, and let this be string 3. So for string 1, the length of string 1, clearly this part goes as or varies as this part x1 minus xp1, and this part varies as x2 minus xp1. So let us write that down first. What do we get? X1 minus xp1 plus x2 minus xp1. This is length of string 1. On double differentiating this, we get a1 plus a2 minus 2 ap1 is equal to 0. So this is one equation that we have. Now for the string, let me do a similar calculation for the string 3. For the string 3 we get x3 minus xp2 plus x4 minus xp2. So this is equal to length of string 3 L3. So on double differentiating we get a3 plus a4 minus 2 ap2 is equal to 0. So this happens to be the equation for string 3. Now talking about string 2, the equation of string 2 or the constraint equation can be written down as xp1 plus xp2 is equal to length of string 2. On double differentiating we get ap1 plus ap2 to be equal to 0. So this is the third constraint equation. So if we multiply this equation with 2 and if we add all the three equations, this, and this, if we add all the three equations after multiplying the third equation with 2, we would get a1 plus a2 plus a3 plus a4 equal to 0. This would be our constraint motion equation. So let me underline it in white. Okay, so the equation for all the masses are simple over here. The tension in the strings are as shown. So this is T, this is T, this is T, this is T, and the tension in this string 2 happens to be 2T. Alright, so for the mass m1 we can simply write m1g minus T is equal to m1 a1. For the mass m2 we can write m2g minus T is equal to m2 a2. For m3 we can write m3g minus T is equal to m3 a3, and for m4 we can write m4g minus T is equal to m4 a4. So these four equations along with the constraint motion equation will solve the system and get us the exact answer for a1, a2, a3, a4 and T.